Have you ever stopped to think about something that seems almost like magic? You taste one tiny spoonful of soup and you just know if the entire pot needs more salt. How does that work? How can one tiny little piece tell you the story of the whole thing? Well, it's not magic, it's actually one of the most powerful ideas in all of statistics. And today, we're going to pull back the curtain and look at the secret, predictable patterns that show up when we look at samples, patterns that emerge from what looks like total, complete randomness.
I mean, seriously, think about this for a second. We see it all the time during election season. You've got a whole country, millions and millions of voters, every single one with their own ideas, their own beliefs, and yet some news channel will pop up and confidently say, our latest poll of 1,000 likely voters shows, and they'll predict the whole thing. How on earth can 1,000 people possibly speak for hundreds of millions? It feels impossible, right? But the answer isn't a lucky guess. It's a deep mathematical truth that shows us that random samples, if you look at them the right way, aren't random at all. They follow a script.
Okay, so before we go any further, let's get our terms straight. It's super simple. First, you've got the population. This is the whole shebang. It's every single voter in the country, every single freezer coming off the assembly line. It is the entire pot of soup. Now, obviously, we can't go in and talk to every single voter or test every single freezer. That would be insane. So instead, we take a sample, and that's our spoonful. It's a small, manageable chunk of the population that we can actually look at and measure. The entire secret sauce of statistics is figuring out the exact relationship between the sample we can see and the population that we can't.
So here's our game plan for today. We're going to start with the basic logic, the whole one spoonful, one pot idea. Then we're going to uncover 3 different really cool patterns that pop up when we take lots of samples. We'll look at the pattern their averages make, the pattern their yes or no answers make, and a third, totally different pattern that tells us about their consistency. And finally, we'll see how a special connection ties all of this together. It's going to be great.
All right, let's jump right in. How do we build this bridge from one little sample to the giant population? The trick isn't to just take one sample and cross our fingers. No, the real genius is in understanding what would happen if we could take sample after sample after sample. It's in understanding the patterns that would show up. So when we grab our sample, our spoonful, we can ask a few different questions about it. We can ask, what's its average value? The mean, like what's the average temperature of our 14 freezers? Or we could ask a yes-no question. What percentage of people in our sample said yes to our survey question? That's what we call a proportion. And finally, we can ask a totally different kind of question. How consistent is the data inside this one sample? Are all the numbers bunched up together, or are they spread all over the map? That's called the variance. Now here's the kicker, the really amazing part. If you just keep taking samples from a population and measure any one of these 3 things, the results you get will start to form a predictable, beautiful pattern. First up, let's look at the pattern made by the averages of our samples. This is probably the most famous pattern in all of statistics. It's the king. It's the foundation for so much science and business, and it's all thanks to an idea with a big name but a simple point: the central limit theorem. So, picture this. Imagine we're doing this experiment right now. We go out to a big city, and our population is all the adult women who live there. Step 1. We grab a random sample of, say, 100 women. Step 2. We measure their height and calculate the average for just that group. We call that average X bar. We write it down. Step 3. Repeat. We throw that sample back, grab a totally new, different random sample of 100 women, and calculate their average height. We do it again, and again, and again. Thousands and thousands of times. Every single time we get a slightly different average. So what happens when we take all of those thousands of different numbers, all those X bars, and we plot them on a chart? What you get is this. Out of all that randomness, this perfect, beautiful, symmetric, bell-shaped curve just emerges. It's called the normal distribution, and this is the magic of the central limit theorem. It doesn't matter what the distribution of heights looked like in the original population. It could have been weird and lumpy, anything at all. The distribution of the sample averages will almost always smooth out into this perfect bell curve. Most of our sample averages will land right near the true average of the whole population, and the further you get from the center, the rarer and rarer those results become. This is it. This is how we turn chaos into predictability. Okay, so knowing this pattern exists is amazing, but the real power comes from using it. And for that, we use something called a z-score. This formula might look a little intimidating, but let's just break it down piece by piece. It's actually telling a very simple story.
The whole point of Z is to give us a standard score that tells us exactly how surprising our sample is. So let's look at the top part, the numerator. You have x bar minus mu. X bar, or x bar, that's the average we got from our one sample, the thing we actually measured. Then we subtract mu, the Greek letter mu. That stands for the true actual average of the entire population, which we usually don't know but want to estimate. So that top part is just asking, how far off was our sample from the real truth? It's the signal. Now look at the bottom, the denominator. This part gives us context for that signal. We have sigma, the Greek letter sigma, which is the standard deviation of the population. That's just a measure of how spread out the population is naturally. Is everyone the same height, or is there a lot of variation? We divide that by the square root of n, and n is just our sample size. Now this whole bottom part is called the standard error. And check this out. The bigger our sample size n gets, the smaller the standard error becomes. That means a 1-inch difference from the true average is way more meaningful if you found it in a sample of 10,000 people than in a sample of 10. So the z-score takes the raw difference we saw on top and it puts it into context using the bottom. It gives us one simple number that tells us how many standard errors away from the mean our result was. Okay, wow. So that's how it works for averages. It's an incredibly powerful pattern. But what if our data isn't a measurement like height or temperature? What if it's just categories? You either pass or you fail. You vote yes or you vote no. You click on the ad or you don't. Well, believe it or not, a very, very similar story is about to play out. So with categorical data, we don't talk about means. We talk about proportions. And the sample proportion is super intuitive. We call it p-hat, and it's written with that little hat on top. The formula is just x over n. X is the number of times the thing we're looking for happened, and n is our total sample size. So if we polled 200 voters and 88 of them say yes to our question, our p-hat is just 88 divided by 200. That's 0.44 or 44%. Simple as that.
And here's where it gets kind of spooky in a cool way. If we do the exact same thing we did before, we take a random sample of 200 voters, calculate our p-hat, write it down, and then we do it again, and thousands of more times. And then we plot all those thousands of different sample proportions. Guess what you get? You get the exact same beautiful bell-shaped normal distribution. It's incredible. Even though we started with simple yes-no data, when you look at the proportions from many samples, that same predictable pattern shows up again. Order from chaos, part 2.
And because the pattern is the same, we can use the same tool, a z-score. And I want you to look at how similar this formula is. It's the same story. On top, we have p-hat minus p. That's our p-hat, the proportion we saw in our sample, minus capital P, the true proportion in the entire population. Again, it's just what we saw minus what's actually true. It's our signal. And on the bottom, we have the standard arrow for proportions. It looks a little different, but it does the exact same job. It gives us context. It tells us how much we should expect these sample proportions to bounce around just by random chance. And look, n, the sample size, is right there in the denominator again. A bigger n makes for a smaller standard error, making any difference you find on top much more significant. It's the same logic, just applied to proportions instead of means. Signal divided by noise.
So why do we do all this? What's the payoff? It's that we can now answer really specific questions with actual probabilities. Let's go back to that voter example. Let's say we know for a fact that true support for Proposition A across the entire population is exactly 40%. That's our capital P. Now we can ask, if we go out and take a new random sample of 200 voters, what is the probability that our result, our p-hat, will land somewhere between 40% and 45%? Well, we just pop 40% and 45% into our z-score formula, find out where they land on that normal curve, and calculate the area between them. And the answer is 0.4251. There's a 42.5% chance of that happening. That's not a guess, it's a precise probability that we calculated because we understand the pattern of random samples. So far, so good. We've seen that both sample means and sample proportions give us that nice, predictable, normal distribution. We've been totally focused on the center of our samples, the average value or the key proportion, but now we're going to ask a third question. What about the spread? How consistent are the data points within a single sample? Let's shift gears for a minute. Think about that freezer factory again. Yeah, it's great if the freezers have the right average temperature, but what if some are freezing cold and others are barely cool? That's a huge problem. Consistency is everything. Quality control is about minimizing variation. So for this new question, we don't care about the average of our sample anymore. We care about its internal consistency. The way we measure this is with a number called the sample variance. We write it as S squared. And all it is a single number that tells you how spread out the data is inside one sample. If the variance is small, it means all the freezers in your sample had very similar temperatures, all clustered together. That's good consistency. If the variance is big, it means the temperatures were all over the place. That's low consistency and probably a big problem.
Okay, so you know the drill. We're going to do our experiment again. We grab a random sample of 14 freezers, and this time we calculate its variance. It's S squared. We write it down. Then we grab another sample, calculate its variance, and another, thousands of times. We take all those different variance numbers, and we plot them. And we're expecting to see that nice bell curve again, right? Well, we don't. This time we get something totally different. We get a skewed shape. It's piled up on the left and has this long, stretched-out tail to the right. It's a whole new pattern.
So what is this weird new shape? It has a name. It's called the chi-square distribution. That's the Greek letter chi squared. And the coolest part is it's not some random new thing. It actually has a deep, direct connection to the normal z distribution that we already know and love.
And this is how it works. It's so clever. On the left, that's our old friend, the standard normal z distribution. Symmetrical, centered on 0, with negative values on the left and positive values on the right. Now, just imagine for a second that you took every single possible z-score and you squared it. What happens? Well, 2 squared is 4. But what's negative 2 squared? It's also 4. Squaring any number, positive or negative, always gives you a positive result. So that whole negative half of the z-distribution, the whole left tail, it basically gets folded over and dumped on top of the positive side. That's what creates the skewed shape. A chi-square distribution is, in a very real sense, born from squaring a normal distribution.
And that brings us to the chi-square formula, which lets us use this pattern. Let's break this one down too. At its heart, it's just a ratio. It's comparing the variance we saw in our sample to the variance we expected. On top, we have S squared, which is the variance we actually calculated from our sample. We multiply that by n-1, where n is our sample size. That n-1 term is called the degrees of freedom, and it just helps adjust the shape of the chi-square curve. Then on the bottom, we have sigma squared, or sigma squared. That's the true variance of the entire population, our benchmark for quality. So this whole formula is just a fraction that tells us how our sample's variance stacks up against the true population variance.
And this is incredibly useful. Back to the freezer factory. The bosses have a strict rule. The variance in temperature across all freezers, our sigma squared, absolutely cannot be more than 16. That's the quality standard. So we pull a random sample of 14 freezers off the line and we measure their variance, our S squared. Using the chi-square distribution, we can figure out a critical value, a line in the sand. We can say if the variance in our sample is higher than this specific number, then it's a huge red flag that the whole production line is out of whack. And this quote from the source material just nails it. After doing the math for a sample of 14, the critical value for the sample variance, our S squared, turns out to be 27.52. So what does that mean in plain English? It means if our little group of 14 freezers has a variance higher than 27.52, we can be statistically confident that the entire production line is failing to meet that quality standard of 16. It's not a guess anymore, it's a data-driven decision.
So let's just take a step back and see what we've done. We've seen that what looks like pure chaos, the randomness of pulling samples, actually has these deep, predictable patterns hiding just beneath the surface. The normal distribution for means and proportions, the chi-square for variance. These are the rules of the game. They tell us what random chance looks like. And that leaves us with one last massive question. If we know what a normal random sample is supposed to look like, what does it mean when we get a sample that breaks the rules? What does it mean when we get a result that's a wild outlier, way out in the tail of the distribution? What is that weird sample trying to tell us? Well, answering that question is the key to the entire world of scientific discovery and hypothesis testing.